Hello, everyone. It's great to be here. So I just want to say a few unanimated words about myself. I'm a professor of computer science at Tel Aviv University, but I actually started my career in computing doing vulnerability research, and then I spent several more years doing security research in the industry. And then I moved to academia, and now I'm interested in all things that are low level and involving software-hardware interactions. So I'm working on everything from computer microarchitecture to operating systems. But as we're going to see, that still tends to involve security as well. One more important thing to note is that everything in this talk is joint work with Ofek Kirchner, who did this research for his master's studies at Tel Aviv University. And we wrote an academic paper about this work. It goes into many details that I won't have time to cover in this talk. So if you find it interesting, I encourage you to look the paper up online and read it for a very deep dive on all the topics that I'm going to be talking about here. So this talk is going to be about speculative execution attacks, which are also called Spectre attacks, and they have this cute logo. And you may remember them a few years ago. There were a lot of headlines in the newspapers about bugs in CPUs, particularly Intel's. So these are these attacks, and these are these bugs. And what we're going to do, I'm going to talk about a specific type of speculative execution attack called Spectre variant 1. And this is a really interesting attack because the CPU vendors said that they are not going to fix it in hardware. What they want to do is for software developers to deploy software mitigations to block these attacks in software. And software developers usually look at this attack as being a certain type of exploit that involves bypassing array bounds checks. And that's how they do the mitigations. But what I'm going to show you is that actually there are many other attack vectors for exploiting Spectre variant 1, and these mitigations that people currently deploy are not always effective. So the takeaway here is going to be that defending from Spectre variant 1 is not a solved problem, and current mitigations may need to be rethought. So let me start with a quick background about Spectre attacks. So in general, a Spectre attack is any attack that uses speculative execution of some gadget, gadget in a victim program in order to steal information from the address space of that program that the attacker doesn't otherwise have access to. So these are not attacks that do code execution. These are information disclosure attacks. They steal information from the victim. And specifically, Spectre variant 1 is the subclass of attacks that uses a conditional branch misprediction for the speculative execution part. And this is usually described as being a bounds check bypass attack, so that's the way I'm going to introduce it here as well. So what happens in this attack is that there is a code gadget in the victim, and there is some value X that the attacker can control, and the victim uses it to index into some array, and because of that, it does a bounds check before indexing into the array. So in the attack, what the attacker does, they start by invoking the victim many times with an inbound value of X that passes the bounds check. And this causes the branch prediction unit of the CPU to learn that the result of this condition is usually true. Then, to perform the attacker causes the CPU to execute this gadget with an out-of-bounds value of X. Now, in order to compute whether X is within bounds or not, the CPU needs to read the length of the array from memory. This takes its time, so in the meanwhile, it predicts what the result of this condition will be. And because of what it learned previously, it predicts that the result is going to be true, so it starts executing this code speculatively. And when it performs this code speculatively, it uses X to index into the array. X is out of bounds, so basically it reads from some address that the attacker specified, and it reads it into this variable Y. Now, in order for Spectre variant 1 to be exploitable, the code gadget needs to have the property that the value that was just read gets passed as an index into another array. And when the CPU executes this second array access speculatively, what happens is that the cache set that the value gets loaded into, the cache set that Z gets loaded into, depends on the value of Y that was read. It depends on the secret that the attacker wanted to read. Okay? And basically, this means that in some sense, the state of the cache now encodes the secret. So eventually, the CPU gets the length of the array from memory and realizes that everything it did until now was because of a misprediction. This is not code that was supposed to execute. So it flushes the pipeline and resumes execution from the condition, this time executing the correct flow of the code. The problem is that, unlike the pipeline, the changes made to the cache state are not flushed. And so the cache state remains dependent on the value of the secret, and this allows the attacker program to use some certain sequence of memory operations that they time in order to decode the secret from the cache state. So one important thing to note is that this last part of decoding the secret from the cache state, this is something called a cache side channel. And more generally, a microarchitectural side channel is any condition in which some state of the CPU, like the cache, or the TLB, or the branch predictor, becomes a function of some secret in a way that allows interacting with this structure and decoding the secret. Okay? But side channels, these are not new. These are not what made Spectre interesting. These were known for a long time in the context of cryptographic attacks. What made Spectre interesting is the ability to use or abuse speculative execution in order to read from anywhere in the victim's program memory and pass that value through a side channel to the attacker. So this is what I'm going to focus in this talk. It's about the ability to read anywhere from memory using speculative execution, not the mechanism that afterwards gets used in order to leak the value. Okay? And you might ask yourselves, where do we find a situation in which an attacker program runs on the same CPU as the victim in order to read from the side channel? And one good answer is the operating system kernel, or specifically in this case Linux. Because the operating system is by definition a program that has to share the CPU with untrusted parties. These are the untrusted, unprivileged processes that the operating system manages. So if we continue this, the example in the context of our operating system, this gadget foo can be something that gets executed in the flow of some system call that the process can invoke. And by exploiting the attack, the process can read from any address in the kernel address space. And this means that basically it can read from any address in the physical memory of the machine because the kernel maps all physical memory into its address space. So this attack allows the process to read from anywhere in memory, read passwords, read credit cards, whatever it wants, it can read from the physical memory. And Spectre variant 1 is caused in some sense by the speculative execution feature of the hardware, but it also requires, like you saw, the victim to have a certain code gadget. So I'm not sure, but perhaps because of this, CPU vendors said that they are not going to fix it in hardware, they are not going to disable speculative execution because it's very important for performance. Instead, they direct developers to use software mitigations in order to block these kinds of attacks. So let's look at what developers did. So what they did in Linux is they use a manual mitigation approach. Basically, if you are a Linux developer, you need, whenever you have an array access, you need to think about, can the index into the array be something that is controlled by an attacker? And if so, you need to use a special API to do the indexing. You don't do regular indexing, you use this array index no spec API. And this is an API that internally makes sure that the access is always going to be within bounds, even under incorrect speculation. And of course, it's a bit slower than a regular array access. Okay? But this mitigation has a conceptual problem because it's only targeting array bounds checking. And if you go back and read the Spectre paper and see the definition of Spectre variant 1, it's much more general. It says that Spectre variant 1 is any case where a branch misprediction causes the CPU to temporarily violate program semantics by executing code that would not have been executed otherwise. So in principle, there can be many other ways to exploit Spectre variant 1. And I'm going to talk about exactly one such way, which is called speculative type confusion. So speculative type confusion is an incorrect execution in which the wrong speculation causes the code to execute with some variables having values of the wrong type. And because of this, the program leaks information. Okay? So let me show you an example. So speculative type confusion was mainly theorized about, and even these theories were in the context of only polymorphic object-oriented code, like in this example. So what we see here is some function that is maybe called by some system call. And the argument to this function is some object from a base class. The function uses the type field in the object to derive a specific type, a subtype of the object. And then it acts accordingly. So if it gets past an object of type 1, it does this code which reads some value from the object and then does some operation that maybe leaks this value over a side channel. Okay? Now, what does speculative type confusion mean? What happens if this function is called with an object of type 2, but because of branch misprediction, the CPU still executes the code of type 1. Then what happens, it's going to read some field, but it's going to be a field in the type 2 object, not type 1, and this field might contain secret information that then is going to get leaked. Okay? So, not sure if you are very impressed by this example, maybe it seems contrived, but the main observation of our work was that speculative type confusion can be much more prevalent than just what this example shows. And in fact, it can be even exist in benign code without the programmer realizing that it's there. So we did an analysis of the Linux kernel looking for speculative type confusion. And we actually found new types of speculative type confusion. We found both exploitable vulnerabilities and latent vulnerabilities, which currently are not exploitable, but they're not exploitable by luck, not by design. And any small code change might make them exploitable. So what I'm going to show you, we found that attackers can introduce vulnerabilities into the Linux eBPF subsystem. We found that the compiler can inadvertently introduce vulnerabilities when compiling benign code. And we found many, many latent vulnerabilities related to polymorphism. So let's start with speculative type confusion in the eBPF subsystem. What is eBPF? eBPF is a feature of Linux which allows unprivileged processes to load small programs into the kernel that then run in kernel context. And this is useful for performance monitoring and all kinds of other things. Of course, it seems also very dangerous, right? We allow untrusted processes to upload code into the kernel. So how is this supposed to be secure? The idea is that the program is written in a special bytecode called an eBPF bytecode, and then gets uploaded into the kernel with a system call. Before the kernel executes the program, it does some analysis to make sure that the program is safe. So one thing the kernel does is it runs a static analysis in order to verify that the program is safe, that it doesn't try to read from kernel memory, that it doesn't have buffer overflows, that running this program will be safe for the kernel. And after Spectre was discovered, they also started adding Spectre mitigations into the bytecode. Specifically for Spectre variant 1, they add mitigations for array bounds checking. So essentially, they put this array index no spec type of thing into the uploaded eBPF code. And after all of this happens, the eBPF bytecode gets compiled into x86 bytecode and x86 native code, which can then run inside the kernel. So what's the problem? What's the vulnerability that we found in eBPF? So let me show you this by example. Consider this eBPF program that can get uploaded into the kernel. What this program does, it reads from some value in memory, from some array. It reads the value into register R0, and then it checks what the value was and acts accordingly. If R0 equals 0, the program does a register-to-register transfer. It overwrites register R6 with the value of register R9, and register R9 initially in the program contains some scalar, some constant, that is attacker controlled because it's part of the program, and remember, the attacker supplies the program. An untrusted process supplies the program. If R0 is not 0, if R0 is 1, the program does something else. It dereferences register R6, which originally points to some local variable on the stack. So it does a read from the stack, and then it uses it to index an array, which also leaks the value, but that's okay because it's some local variable on the stack. It doesn't contain anything sensitive. Okay, so this is the program. Now, what does the eBPF verifier do in order to decide that this program is safe to run? The way it works is that it basically enumerates all possible executions of the program, checks that each execution is safe, and if all executions are safe, then it lets the program execute. So let's see what it does. First, it looks into the execution in which the first condition evaluates to false. In this case, it means that what the program does is a register-to-register transfer. This is safe. And the eBPF verifier also learns that R0 must be 0. And because of this, it cannot be that the second condition evaluates to false. So overall, this execution is considered to be safe. Another possible execution is the one in which the first condition evaluates to true, and the second condition evaluates to false. In this execution, the program reads from memory, which is potentially risky, but the eBPF verifier knows that R6 points to a local variable on the stack, so this is also okay, and it considers this execution safe as well. And finally, there is an execution in which both of these conditions evaluate to true, so the program does basically nothing, and of course this is safe. Overall, the eBPF verifier checked all the flows, and it concludes that this is a safe program to execute. But what's the issue? What's the vulnerability? The problem is that the verifier doesn't consider flows that can happen because of speculative execution, incorrect flows that can happen because of speculative execution. And if we have an execution in which the first condition is predicted false, and the second condition is also predicted false, then we get this kind of funny execution in which R0 is both 0 and 1, and the sequence of instructions that the CPU will speculatively execute will put R9 into R6, so R6 will now have an attacker-controlled scalar, dereference R6, so read from the address the attacker supplied, and then leak it over a side channel, and this allows the attacker to read from anywhere in physical memory. Okay? What's the problem? The main challenge of making this attack work? How do we get the CPU to do this kind of prediction, predicting that both of these branches will be false? And the issue is that if you try to do something like what I described earlier, basically running the program many times, giving it values, hoping that the branch predictor will learn the outcome that we want, this will never work because these branches are mutually exclusive. If the first one evaluates to false, then the second one will not evaluate to false, and vice versa. So no matter how you run this program, the branch predictor will never be convinced that both of these branches should be false, both of the conditions should be false in the same time. So to solve this challenge, we use a technique called out-of-place training. Instead of running the actual, invoking the actual eBPF program, we allocate some code gadget in the address space of the attacking process. This is called the shadow gadget. It contains exactly the same x86 code that the compiled eBPF code will contain, with one small difference. The conditions here are slightly different. They are now, instead of mutually exclusive, they are the same condition. And then it's automatically the case that if one of them is false, then both of them are false. And the trick is that the address in the process memory where we put the shadow gadget is picked very carefully so that the branch predictor unit entries that these branches map to are exactly the same branch predictor unit entries that the branches in the eBPF code in the kernel map to. The CPU only has one branch predictor, so everything maps to the same branch predictor unit. And this means that by training the shadow gadget, we also influence, actually determine, the decisions that the branch predictor will make when it executes the eBPF program in the kernel. So after doing this kind of training, we can actually perform the attack that I just described. Well, there's a lot more work involved, but that's the high-level idea. And we are able to have an unprivileged process read from any address in physical memory at a rate of 6.5 kilobytes per second, which doesn't sound like a lot, but for a side channel, it's not bad. Okay? And this is something that we disclosed to the Linux community, and it was fixed a few months ago. Next, I'm going to talk about compiler-introduced speculative type confusion. So the observation here is that benign code the compiler might inadvertently introduce speculative type confusion vulnerabilities into completely benign code because the compiler does optimizations that depend on reasoning about only correct flows and not incorrect flows. So let me show you an example. Let's consider this flow. This is a C function that maybe exists in the kernel. It has these two mutually exclusive conditions, similar to what we have in the eBPF gadget. And in the second condition, it dereferences some pointer, which is trusted. It's a kernel supplied pointer. Now, when the compiler compiles this code, it might reason that because these branches are mutually exclusive, it doesn't, if the first condition is true, then nothing that happens inside this if block can affect what happens in the second block. So the compiler might put here some code that overwrites register RSI, which is the register that contains the PTR argument, overwrite it with some value, a scalar value x, that is controlled by an attacker, that is not trusted by the kernel. And then you know what's coming next. If an attacker is able to train the branches such that both of them predict to be true, then we get an execution in which the value x is written to RSI, and then the CPU continues and happily executes the dereference, but instead of dereferencing the PTR argument, it dereferences the attacker supplied address x, leaks the value, and again, allows the attacker to read from anywhere in physical memory. Okay, and the scary thing about this example is that the untrusted value x is not used in any dangerous way in the code. It's not an index into an array. Nothing depends on it here. And so a programmer looking at this code would have no idea that they need to put some manual mitigation in order to stop speculative execution attacks. Now, we came up with this example and we wanted to see, does it actually happen in the kernel, in real life? So we ran a binary analysis of multiple Linux binaries, and we focused on analyzing the code of system calls, because that's the main way for processes to interact with the kernel. And the thing that we looked for is the ability of speculative execution to read from an attacker's supplied value. We didn't really care if it gets leaked afterwards, because there are many ways for things to leak, and it can depend on how the code changes over time. The interesting thing here is, can the attacker break the architectural contract and make the kernel read from an address they supply? And the summary of our results is that we've actually found compiler-introduced vulnerabilities in the kernel, and interestingly, they were not like the example that I just gave. They were different. So let me show you a couple of examples. So one gadget that we found quite a few instances of looks something like this. You have a system call that takes some pointer supplied by user space, and it checks if the pointer is not null, then it copies it. This is a safe copy from user memory into kernel memory, copies it into some local variable on the stack. And then it passes it to some helper function. And if the user pointer is null, then the helper function is called with the value null. Okay? So this looks okay, this looks safe. But now let's look at how this code gets compiled. And if you look at the assembly, what happens is that the user pointer is in the RDI register, which is the RDI that the register that is used to hold the first argument of a function. So what the compiler does is it checks if RDI is null, and if so, it immediately jumps to the helper function. It doesn't do what the C code would make you think, which is pass null, write the argument to be null. It uses the knowledge that it just tested that RDI is null and invokes the helper function, passing it RDI. And if RDI is not null, then it goes into some code that does the memory copy, and in the end, it moves the stack pointer into RDI so that the function runs, and this time the argument will be the pointer to the stack variable. And now I hope you can see what the problem here is, which is if we run this system call with a non-null pointer, but the branch gets mispredicted to jump to the function immediately, like in the null case, we get again a funny execution in which RDA is not null, but the code of RDA null gets run, and the helper is called with the attacker supplied address, and potentially could, it does dereference it, and it potentially could also leak it. Okay? And another interesting gadget that we found happened to be not exploitable, but by luck. And I want to show it because it's very interesting how insidious these gadgets are and how hard it is for a programmer to look at code and figure out if it's safe or not. So this is a function called from the keyctl system call. And it calls a helper function, passing it a pointer to some local stack variable. And the idea is that this helper is going to write a value to this variable. And after the function returns, if there was no error, then this variable gets passed to another helper function, and inside it dereferences this local variable. Okay? So again, this looks very safe. But now, look at what happens when this code gets compiled with a GCC flag that says optimize for minimal code size. What we see is that the space on the stack for the local variable is not allocated by subtracting from the stack pointer, like you would expect. It's allocated by pushing the RCX register, because a push RCX is a 1-byte opcode, and subtracting from the stack is a 4-byte opcode. And it so happens that RCX is a caller-saved register that contains an attacker-supplied value in the caller context. So now, what would happen if the function, the first helper would return an error, so it wouldn't touch the local variable that got passed to it, this dest keyring variable, and the error checking branch gets mispredicted to, instead of taking the error flow, call the second helper anyway. What happens is that the value of the local variable is read from the stack. Since it wasn't updated by the helper function, the value read is the original value of RCX, which was attacker controlled from the caller context. And again, we get a function call in the kernel that executes speculatively on an attacker-supplied pointer. And the only reason that this was not exploitable is because it turned out that the first helper was, I don't know, maybe paranoid, and it took care to overwrite this output parameter on every flow. So there was no way to go into this function and go out without overwriting the value of the output parameter. But of course, this is not something that has to happen. And if somebody changes this code, or if something similar happens in another place in the kernel where they don't do this, then this would be completely exploitable. And how could a programmer look at this and figure out that something is going on because the way the compiler decided to compile a stack allocation of a local variable? It's very hard. And finally, I want to talk about a speculative type confusion related to polymorphism in the kernel. And the funny thing about this analysis is that the problem is caused by another Spectre mitigation, this time of another variant called Spectre variant 2. So Spectre variant 2 is about exploiting the misprediction of indirect call targets. So it tries to predict where an indirect call will jump to. And the attack was able to get indirect calls to jump to any location, to arbitrary locations. The way this is mitigated in software is by replacing indirect call opcodes with a short code segment called a retpoline. And the retpoline executes the indirect call, but it does it in a way that is speculation safe, which is another way of saying that it disables speculation in software. So this is safe, but there's a huge performance penalty. And because of this, Linux started moving in the direction of replacing certain code locations, certain indirect calls, replacing retpolines with another approach. This is an approach that instead of disabling speculation, has a sequence of checks that the address read from memory, which the function is supposed to jump to, is one of a set of possible targets. And if so, it jumps directly to that address. So what happens is that now speculation is possible because we have these jumps, but mispeculation, misprediction can only cause the kernel to go into one of a set of legal targets. So not any arbitrary address like in Spectre v2, but one of a set of valid targets. Unfortunately, this can still be vulnerable to speculative type confusion. And let me show you how. So the problem comes from the way that Linux does data inheritance and polymorphism in C. So in many locations, there is this structure where there is some common interface, like the API of a file system or the API of some driver. And the specific modules define their own structures that start with a common interface, and then they extend it with their own fields. So in this example, we have module A that has a field with a trusted pointer, and module B that has a field with an untrusted scalar. Maybe this is something that can be set from user space by an IOCTL or something. And the idea is that there is some code path that gets past the common interface that belongs to the specific module, and dereferences it to find the module-specific method to execute, and then it executes it. So, for example, the method of module A would cast the common structure into its module-specific structure, then dereference the pointer, and potentially do something that leaks it. Okay? And module B will do something similar, but with its own field. But now, let's think about what happens if this code, instead of being done securely with a retpoline, is done by checking, is the method equal to foo A, then jump to foo A? Is it equal to foo B, then jump to foo B? Then what can happen is that this code gets executed with the pointer, the argument pointing to a structure of module B, but maybe the branch mispredicts, or the attacker causes the branch to mispredict, and cause the CPU to execute the method of module A. And then what happens? Module A will dereference what it thinks is the pointer, the trusted pointer field in the structure, but since it got past the structure of module B, it's actually going to use an attacker-controlled value, dereference it, and leak it like we saw several times in this talk. Okay, so we wanted to check how problematic this approach might be if Linux extends it from just a handful of indirect calls to maybe all indirect calls. So we did a source-level analysis of indirect calls in Linux, looking for these types of cases where you have two functions with the same interface. One of them has a pointer dereference, and the second has a scalar, attacker-controlled scalar at the same offset in the structure, which would make this kind of thing exploitable. And we actually found that there are thousands examples like this of potentially vulnerable function pairs. Of these, hundreds actually use the value that is dereferenced and pass it as an index to another array. So they actually leak the value. And we looked at these manually and concluded, not with 100% certainty, but it seemed to us that despite that, the fact that there are a lot of these, they seem to be not exploitable, again by luck, because maybe the value that the attacker controlled, they don't have full control. So they can't put a pointer there, either because the kernel limits what they put there, or because it's too small, it's a 16-bit value and not a 64-bit value. All these kind of things that can change from one version to another potentially become exploitable. Let me show you an example. So here is an actual method of a driver from Linux. It accepts a struct device. This is the common structure, converts it to the model-specific structure, and prints a value of some field called max frequency. And now let's look at the same method from another driver, the USB driver. What it does is it converts the structure, the shared structure, into a module-specific structure. But this time, it dereferences some pointer in a field called cap, and it passes the value that was read as an array index into some array. And the cap field is in exactly the same offset as the max frequency field. So this would be exploitable, but for the fact that if you look at how this max field is set, then it's through some function, some IOCTL that doesn't take the value directly from the attacker, but it sets it into one of some pre-selected small set of values. So the attacker can't put an arbitrary address there. But again, if this changes or something similar happens in another module, this would be exploitable. So the conclusion from this is that right now, this type of thing is not done in a lot of indirect calls, but if they extend this and start doing it in many indirect calls, then this would put the security of the kernel on very shaky ground, because anytime a small code change happens, this might create a vulnerability, and you can't really expect somebody working on the USB driver to go and check all the other drivers that use the same interface and see if there is a potential speculative type confusion happening there. So I want to emphasize that all of this was done with pretty naive analysis, static analysis. It was not exhaustive. It could have false negatives, and it could have false positives. So I think that there is much more room for improvement here, and potentially there are a lot more vulnerabilities to be found. And concluding, where does that put us in terms of mitigating Spectre variant 1? So the manual approach doesn't seem to be workable given all of these insidious gadgets. Fortunately, there are comprehensive protections that can be enabled in a compiler. For example, LLVM has something called speculative load hardening, but these are comprehensive because they protect every branch in the program. So they have a lot of overhead. We did a benchmark of Linux with SLH enabled, and we saw that system calls got slowed down by an average 1.5x, sometimes even 2.5x. So this doesn't seem like an acceptable overhead. And so I think that it might be the case that there's no choice and hardware needs to help. So maybe not disable speculative execution, but do something that helps software mitigations maybe become more efficient. And to conclude, I showed you that speculative type confusion vulnerabilities exist in the wild, both exploitable and latent vulnerabilities. These gadgets are very insidious. They can materialize because of compiler optimization. Programmers have a very hard time of reasoning about them. And so the takeaways is that if you are an attacker, go look for these. I think the analysis we did is just the first step. And if you're a defender, we need to rethink how we are defending for Spectre variant 1. It's not a solved problem. Thank you very much. It was a pleasure.